In the quiet hum of server rooms across the world, billions of bits are flowing every second. Zeros and ones, the lifeblood of our digital civilization. Everything we do, every message we send, every photo we share, every online transaction, it's all encoded in binary, guarded by encryption that has, so far, stood the test of time. But somewhere in the labs of IBM, Google, and a handful of secret government facilities, another kind of machine is awakening, one that doesn't play by the same rules. It doesn't think in zeros or ones, but in infinite possibilities between them. This is quantum computing, a technology that could rewrite everything we know about data, communication, and security. Some call it the greatest leap in computing since the invention of the transistor. Others warn it could shatter our digital defenses overnight, breaking encryption, exposing secrets, and rendering decades of cybersecurity obsolete. This is the story of how quantum computing might transform or destabilize the entire future of data. To understand the power of quantum computing, we need to step back all the way to the strange world of quantum mechanics. In the early 20th century, scientists like Max Planck, Albert Einstein, and Niels Bohr uncovered a bizarre truth. The universe, at its smallest scales, doesn't behave like the solid, predictable world we see around us. Particles can be in two places at once. They can tunnel through barriers. And most shockingly, their behavior changes just by being observed. It's a world where logic bends and probability rules. Now imagine building a computer that doesn't just simulate this world, but uses it directly to compute. That's what a quantum computer does. Instead of bits that are strictly 0 or 1, quantum computers use qubits, quantum bits, which can exist as 0, 1, or both at the same time, thanks to a property called superposition. And when qubits become linked, a phenomenon known as entanglement, they can influence each other instantly, even across vast distances. This is the foundation of a new kind of machine, one capable of processing vast amounts of information simultaneously, solving problems that would take classical computers millions of years. For decades, quantum computing was a theoretical dream, too unstable, too sensitive to noise, too delicate to be practical. But slowly, quietly, the dream began to take shape. In the early 2000s, research labs began building experimental systems. Companies like D-Wave created the first quantum annealers, limited but real. By the 2010s, IBM, Google, and Rigetti had entered the race, developing superconducting qubits that could be cooled near absolute zero. In 2019, Google made headlines when it announced quantum supremacy. Their 54-qubit computer, Sycamore, completed a calculation in 200 seconds that would have taken the world's most powerful supercomputer 10,000 years. Though the result was mostly symbolic, it marked a turning point, proof that quantum computing wasn't science fiction anymore. By 2025, the landscape has shifted even further. Governments are investing billions. Tech giants are competing fiercely. The quantum race is no longer academic, it's geopolitical. To understand why quantum computers are so powerful, let's think about how they calculate. A classical computer solves problems step by step, testing one possibility at a time. A quantum computer, on the other hand, can process all possibilities, simultaneously exploring multiple solutions at once, then collapsing into the correct answer when measured. It's like having not one chess player, but every possible chess player playing every possible game, and then instantly finding the one that wins. This is made possible by quantum algorithms, specialized sets of instructions that exploit superposition and entanglement to achieve speed-ups unimaginable by classical means. The most famous of these is Shor's algorithm, developed in 1994 by mathematician Peter Shor. Shor showed that a quantum computer could factor large numbers exponentially faster than classical computers, a task central to modern encryption systems. In theory, a powerful enough quantum computer could break the cryptography that protects everything from banking systems to nuclear codes. This realization sent a shockwave through the world of cybersecurity. Before we understand the quantum threat, let's first look at how cybersecurity works today. Most of the internet relies on public key cryptography. Specifically, systems like RSA, Diffie-Hellman, and elliptic curve cryptography, ECC. These systems are based on mathematical problems that are easy to do one way, but nearly impossible to reverse. For example, multiplying two large prime numbers together is simple. But given the result, trying to find the original primes is practically impossible for a classical computer. That's what keeps your online transactions safe. It would take billions of years for even supercomputers to break that encryption by brute force. But in the quantum world, billions of years can collapse into minutes. When Peter Shor revealed his algorithm, it was a mathematical bombshell. Shor's algorithm showed that a quantum computer could factor large numbers, the very heart of RSA encryption, exponentially faster. If a quantum machine had even a few thousand error-corrected qubits, it could decrypt nearly every piece of protected data on the planet. Every bank record, every private message, every government file. The encrypted skeleton of the internet would be exposed. Right now, most encryption uses 2048-bit or 4096-bit keys. For classical computer, breaking them is impossible. For quantum one, it's just a matter of scale. Scientists estimate that around 4,000 error-corrected qubits would be enough to break RSA 2048 encryption. Current systems only have around 100 to 400 noisy qubits. But the trend is clear and accelerating. We may be only a decade away from quantum decryption becoming a real, tangible threat. To counter this threat, researchers are racing to develop quantum-resistant encryption, also known as post-quantum cryptography, PQC. In 2022, the U.S. National Institute of Standards and Technology, NIST, began selecting algorithms designed to survive quantum attacks. Names like Kyber, Dilithium, Falcon, and Sphinx Plus emerged as frontrunners. Mathematical systems based on lattice problems, error-correcting codes, and hash functions that even quantum computers struggle to solve. Governments and corporations are already beginning the migration, a process known as crypto agility. It's a digital arms race, where every line of defense must be rewritten before quantum systems mature enough to strike. Even though large-scale quantum computers aren't here yet, a silent danger already exists: data harvesting. Hackers, state actors, and intelligence agencies are collecting encrypted data today. Banking files, diplomatic communications, personal messages, with the intention of decrypting them once quantum computers are powerful enough. It's called the harvest now, decrypt later strategy. In other words, the data you encrypt today may not stay secret tomorrow. This raises critical ethical and national security questions. How long should data remain private? How much of our digital history will quantum technology unlock? For cybersecurity professionals, the quantum clock is ticking. While quantum computing threatens encryption, it also offers a defense: quantum communication. The same principles that make qubits powerful also make them secure. Enter quantum key distribution, QKD, a revolutionary way to transmit encryption keys using entangled photons. If anyone tries to intercept or measure those photons, their quantum state collapses, immediately revealing the eavesdropper. In essence, it's encryption guaranteed by the laws of physics, not mathematics. China has already demonstrated this technology on a continental scale, building a 2,000-kilometer quantum communication line between Beijing and Shanghai, and even launching a quantum satellite named Mischius to test secure communication from space. In the coming decades, we may see the birth of a quantum internet, a network immune to interception, using photons instead of electrons, secured by the universe itself. Quantum computing won't just change cybersecurity. It will change the entire ecosystem of data and intelligence. In artificial intelligence, quantum algorithms could process complex datasets exponentially faster, unlocking new patterns in weather, biology, and economics. In medicine, they could simulate molecular interactions at atomic levels, speeding drug discovery by decades. In finance, quantum models could analyze entire market systems in real time. But this power comes with risk. Quantum AI, combined with advanced data access, could make surveillance systems unimaginably precise, tracking patterns in everything from social behavior to genetic data. The line between innovation and intrusion will blur. The quantum race is not just scientific, it's strategic. The first nation to achieve scalable, fault-tolerant quantum computing will gain unprecedented power. The ability to decrypt global communications, optimize logistics, and defense systems, dominate AI modeling, and potentially rewrite the balance of digital power. The United States, China, and the European Union are leading the race. China's 14th five-year plan explicitly names quantum technology as a top priority. The U.S. has launched the National Quantum Initiative, investing billions into research. This is the new arms race, not for nuclear dominance, but quantum supremacy. As quantum technology evolves, so too will the ethical dilemmas surrounding it. Who controls quantum computing power? Who decides which data should be decrypted or protected? And how can society ensure that privacy remains a right, not a relic? Quantum technology could either fortify digital democracy or empower authoritarian surveillance. It could safeguard human rights or violate them. The direction we take depends on how responsibly we develop and regulate this power. The quantum revolution will also reshape industries. Financial institutions are already testing quantum-safe systems. Cloud providers like Amazon and Microsoft are offering quantum-as-a-service platforms. Startups are emerging to fill niches, from quantum hardware to simulation software. By some estimates, the global quantum computing market could surpass $450 billion by 2040. But more than money, it's the data economy that will change. Quantum data, entangled, probabilistic, and powerful, will become a new kind of currency. The path forward isn't just about faster computers. It's about redefining trust in a post-quantum world. Every institution, from governments to private companies, will need to rethink how they store data, how they encrypt it, how long it must remain secure. We're entering an era where security will no longer mean unbreakable, but quantum resilient. The migration won't be easy. It will take decades of re-engineering the world's digital infrastructure. But it's a race we must win before the machines do. Quantum computing isn't just a technological shift, it's a philosophical one. It forces us to rethink the nature of information, reality, and uncertainty. In a classical world, data is definite. In the quantum world, it's probabilistic, a mirror of our own universe, where truth exists in superposition until observed. The computer of the future won't just calculate. It will understand possibility itself. And perhaps, in that uncertainty, lies a deeper reflection of human consciousness, a reminder that even in logic, mystery remains. In the end, the story of quantum computing is the story of humanity's constant desire to transcend its own limits. From the first abacus to the silicon chip, every leap in computing has redefined our world. Quantum is the next leap, but it's also a crossroads. It could secure the unbreakable internet or destroy it. It could make data eternal or meaningless. It could elevate our understanding of the universe or expose the fragility of our digital civilization. The quantum era is coming, not as a whisper, but as a revolution. And when it arrives, the rules of cybersecurity, privacy, and trust will be rewritten in the language of qubits and entanglement. The question is not if it will change the future of data. The question is, are we ready for it?